Hey, so I'm Joe, and this is the fourth video for the seventh chapter of Stewart's Calculus, and we're going to be talking about improper integrals. And so, there are a couple of types of improper integrals, and the first type is called an infinite improper integral, and that is when we have an infinite interval of convergence. That means that on one of the limits on the integrand is going to be either an infinity or a negative infinity, and we call this improper because that's not actually a number, that's something that you approach. And so we can express this, when we write the integral out in this notation, it's actually improper notation because that's not a real number. We need to express it as a limit. So the way that we would express this to make it proper, we would write out the limit as t approaches infinity, because we can use an infinity, we can approach infinity, that's proper limit notation, and then put a t on the integrand where the infinity should go, a 1, and then we have f of x dx. And that's the proper notation for an improper integral. But the reason that an infinite improper integral is important is it allows us to ask the question, can we ever find a definite area under a curve over an infinite interval such that an infinite integral like this will actually equal a real number? And that seems kind of weird because you say, well, wait, that curve will go on forever. Essentially, like theoretically, you would be adding infinite area. And so how could you ever get anything else than infinity out of that? Well, turns out you actually can. Sometimes you will get a real number. And when you do get that real number, you say that the integral converges. It converges to an actual value. And when it doesn't, you say that it diverges. And so two of the most common kind of examples for this, for a convergent and a divergent infinite integral, are the following. A convergent one is when you have the limit as t approaches infinity between 1 and infinity, that's in proper notation, between 1 and t of 1 over x squared dx converges. We'll actually get an area, a definite number out of this. But the limit as t approaches infinity of between 1 and t of 1 over x, that diverges. And you might think that's a little weird. Those functions seem super similar. Why does one converge and one diverge? Well, we have two kind of explanations for this. The first one is the algebraic explanation. Let's actually try to solve these integrals and see what comes out of them. And then there's an intuitive explanation that involves graphs and Excel. So first off, I'm going to show you the kind of intuitive explanation for why this integral right here converges, and we're going to use Excel. So in Excel, here we have a bunch of x values, and then the area that's going to be under the curve 1 over x squared, and we're going to be starting and it's the integral 1 to infinity, and the infinity is going to be represented by the fact that I'm going to make x get super, super, super big. And we'll see that this area will approach an actual certain value. So let's put 2 into there, and let's draw this down to 30. And then the area, this gets to 30. Okay, so you see that the area is making big jumps here, and then the jumps start to get smaller and smaller and smaller till it gets to 0.96666. And so let's make the step bigger. Let's get to bigger values and see if this ever gets super large. Alright, let's get down to 210. Seems like a good value. We'll bring the area down. Okay, when the area is 210, we get to 0.995. That's almost 1. And we can keep getting even larger. Let's put 600 here. 0.998. So it seems like this, as we get closer to infinity, this just keeps getting closer to 1. There's a single value that the integral seems to converge at. And we can look at the graph of this function. So here's 1 over x, and here is 1 over x squared. The 1 over x squared is smaller than 1 over x. And so what that tells us, that XL graph, it tells us that the area between 1 and, as we keep going, that area will just start converging at 1. Where we'll actually get a definite area of 1. And this 1 over x, this area will keep getting infinitely large. It'll never converge at a value. And so, you say, oh, I want proof, right? We don't see that much of the x-axis right here. This 1 over x, it looks like eventually it'll get so close to the x-axis that it's going to have to converge. Well, we can go over and do the algebra, and you'll see that we're actually, an infinity will come out of the integral between 1 and infinity of 1 over x, whereas we'll actually get a value, and you might guess that it's going to be 1 because it will be 1, as we saw with the Excel spreadsheet right there, when we do the same thing for 1 over x squared here. Okay, so we're going to write out the limit as t approaches infinity, the integral between 1 and infinity of 1 over x squared dx, and we can think of this 1 over x squared as x to the negative 2, and so when we integrate that, well, we got to carry over our limit talk here. When we integrate that, we're going to get a negative 1, and then a 1 over x between 1 and t. And I'm sorry, I put the infinity there. That's supposed to be a t. And then when we do our subtraction here, we're going to get negative 1 over t, minus and a minus is a plus, so plus 1. And this is still the limit as t approaches infinity. And so, when we have an infinity in the denominator, that value starts approaching 0, because if you make a denominator get really, really huge, that whole value eventually is going to get to 0. So, when we write out 1 over infinity plus 1, that's really 0 plus 1, and we'll get a 1. So that means, since we're getting this definite value, we know that this integral converges. And we also saw, and so that means that graph, that area between 1 and forever is going to eventually become 1. And also the Excel spreadsheet kind of intuitively will confirm this. Now let me show you that 1 over x over the same interval does not converge, it diverges. So we'll write it in proper notation. This is very important. On the AP, they will ding you if you put an infinity on the integrand. You have to show that you know that it's actually a limit. So 1 between 1 and infinity, 1 over x dx. So we integrate this, and we will get, gosh, I'm sorry, I keep putting the infinity there. It is a t. It is a t. Don't make the same mistake as me. The limit as t approaches infinity. We integrate, we'll get the natural log of the absolute value of x between 1 and t. And so we put the t in there, we will get the natural log of the absolute value of t minus the natural log of the absolute value of 1. We don't really need to write the absolute value. We know that the natural log of 1 is going to be 0. So minus 0, and we put the infinity in there, the natural log of infinity. So if you imagine a natural log curve, we've got our axes, it looks kind of like this. Even though this slope looks kind of shallow, as x approaches infinity, y will continue to approach infinity. It'll never converge at like a single value like logistic growth or anything like that. It'll keep going up and up and up and up and up. It'll go up and up and up slowly, but it'll keep going. So natural log of infinity is equal to infinity. So we'll get an infinity right here. Since that's not an actual number, that means that this integral diverges. So remember that on an infinite interval, 1 over x diverges, but 1 over x squared converges. And there's a handy rule that you can use that's in your book. So if we have a function that's 1 over to the x to the p, and it's between 1 and infinity. Sorry, I'm writing this improperly. Your book does it sometimes too. But if p is greater than 1, that integral will converge. So if we're integrating x to the third, x to the fourth, x to the fifth, that integral converges. And that is also confirmed by what we call the comparison theorem. This theorem is best explained by the graph that I was showing you earlier. So we've got y equals 1 over x, and we know that that diverges algebraically. We've got 1 over x squared, and we know that that converges algebraically and otherwise. And if you see between 1 and infinity, 1 over x squared is always smaller than 1 over x. So if you say, okay, well that area is going to be a definite number, you would think that an area that's smaller than that is also going to be a definite number. It'll just be a fraction of the area of this larger area. So say we get 1 over x to the x cubed, and that between 1 and infinity is always smaller than 1 over x squared, and 1 over x squared always converges. So just intuitively we should say, alright, well 1 over x cubed has to converge. And that's a correct intuition. That's the basis of the convergence theorem. The convergence theorem tells us that if we have two functions, we have f of x and g of x, and over some interval, f of x is always greater than or equal to g of x. If f of x converges, then g of x has to converge as well. And kind of the opposite goes. If we have this setup and g of x diverges, and g of x is the smaller function, we've got f of x that's always greater than or equal to, then f of x has to diverge as well. And so this is a pretty helpful theorem when we're just looking at integrals. If you have one integral that you don't really know how to solve, but it looks kind of similar to another one that you know is either divergent or convergent, if you establish that the integral at hand is larger than or greater than, you can learn something about its convergence or its divergence. So that's the first kind of improper integral. We've got these infinite integrals. The second kind are discontinuous integrals. So discontinuous integrals, the name is kind of self-explanatory. It's when there's a discontinuity on the interval of integration. And there are two different kinds of cases of this kind of improper integral. We've got the kind where the discontinuity happens on the endpoints of the integral. So if we have an integral like this, the limit as t approaches 2, between 2 and 5 of dx over root x minus 2. So a 2, if we plug 2 in for here, that function is undefined, and so the discontinuity is on the interval, and so because, oh sorry, we got the t here, and so we have to express this as a limit because it's an improper integral. That 2 doesn't really exist on this function, so since we can approach things that don't exist on a function, we're fine, but because it was on there, we couldn't do that. So that's the first kind of discontinuous integral. The second kind is where the discontinuity is in between the two intervals. So that would be something like the integral between 0 and 3 of dx over x minus 1. So the discontinuity is going to happen at x equals 1, and so writing out this integral is improper because this is not a continuous function. So you need to write this as two separate integrals. So we can write it as t approaches 1 from the negative side, we go 0 to t, because we're integrating 0, you go a third, we go a half, we go 2/3, and then we're going to get to 1 eventually, but we're coming from the negative side, so you have to add that negative in there, and then of the same function, and then you add to that the limit as you approach t from the positive, as you approach 1 from the positive side, and you're going to get between t and 3 of the function, because we never actually get to 1, but we're only getting up to the positive side of 1. So that is how you would find that area using kind of the improper integral notation. So now that we've talked about the two kinds of improper integrals, I'm going to go through solving two examples with you. Now the hardest part about solving improper integrals isn't actually this theoretical stuff. This is just notation, really. The hardest part is actually solving the integrals, because now in your book and on the AP, they'll assume that you know how to use all the advanced integration techniques. So the hardest part is figuring out how to solve the integral best, and then kind of doing the conceptual work with the infinite interval of convergence, and then dealing with discontinuities like asymptotes and holes like this, and sort of figuring out whether you will be able to get a convergent or a divergent integral. And remember, you can still get divergent integrals here if this 0, once you solve everything out, or the 1, I should say, once you start solving everything out, will yield an infinity in the answer. If there's an infinity in your answer, it's going to always diverge. That's just a fact. And sometimes the limit doesn't exist. Remember, limits don't exist sometimes if you get a 0 in a denominator. So anyways, let's solve some problems. Okay, so first we're going to solve number 21 on page 551 in your book. And these problems, what they ask us to do is determine whether or not the integral is convergent or divergent, and if it's convergent, you got to evaluate it because there's going to be a number there. And so in your book, they write out the improper integral, an infinite one, like this, with improper notation. So the first thing you have to do is show that you know that that notation is improper, and they're going to do this to you on the AP, by the way. And so you have to prove that it's actually a limit. The limit is t approaches infinity between 1 and t, there you go, I got the t, of the natural log of x over x dx. And we know, yeah. So, first thing we got to do when we solve this is say, alright, what method of integration am I going to use? Well, then the first thing you should ask yourself is, can I use a u substitution? Because that's going to be the easiest. And then you actually can, because when you take the derivative of the natural log of x, you get 1 over x, and we see an x in the denominator. So we'll make u equal the natural log of x, we'll make du equal 1 over x dx, and so this will equal the limit as t approaches infinity, and 1, we put a 1 in there. The natural log of 1 is going to be 0. Natural log of infinity is still infinity, so that infinity is fine. And we will get u du. And this is going to be pretty easy to solve. We're going to get u squared over 2 between 0 and t. The limit as t approaches infinity. And then we're going to get t squared over 2, so that's going to be infinity squared over 2. You do anything to infinity for the most part, unless, aside from having it in the denominator, and it's going to still be infinity. You're going to subtract a 0 from that. So this is infinity, that means it is divergent. The area under that curve is going to keep growing forever as x approaches infinity. So that's kind of the easiest version of this problem. Simple integral to solve. We just get an infinity out immediately, and we figure out that it diverges. So now let's do a sort of different kind of problem. Alright, we're going to do number 14, and we're asked to solve this improper integral, also in infinite interval. So immediately, what we have to do is we have to write out that we know it's a limit because it's infinite, so that's going to be as t approaches infinity between 1 and infinity of e to the negative root x over root x dx. So, again, what we need to ask ourselves is, how are we going to solve this? And first thing that should pop into our mind is, let's try a u substitution. What could we make for u that we'd be able to find its derivative somewhere else in the function? Well, we take the derivative of this expression here. We don't see an e anywhere else. That can't be our u. We try u of root x. We don't, or of x to the negative 1/2. We don't see a root x anywhere else, just lying around. So it can't be that. What about if we try to do u equal negative root x? Well, we do see an x to the negative 1/2 down in the bottom. So it looks like that's good. We can do a u substitution. So we make u equal negative root x, du will equal negative 1 over 2 root x dx. We don't see this negative in the function, and we don't see the 1 over 2. So we're going to need to deal with that in the coefficient. We put in negative 2, and then we will have the oh gosh, I'm sorry, I keep putting the infinity there, between 1 and t of e to the u du. There you go, because we already took care of this with the du. And this means that this 1, is this 1 still good? Negative, no. That will end up being a negative 1 right there. And then the t, you put an infinity into root x like this, negative. Well, that would actually be negative infinity, but what we can do is we can just write out like that. Negative e to the u, and so when we integrate this, we're going to get the limit as t approaches infinity so we integrate e to the u, and that's just going to give us another e to the u, so negative 2 e to the negative root x, and then we'll get our old limits back because we're back in terms of x, between 1 and t. And so when we put an infinity in here, this exponent means that this e is actually in the denominator. So we're going to get negative 2 e to the root infinity minus and a minus is a plus 2 e to the root 1, so that's e to the 1. So this whole term down here is going to become an infinity. That means that that's a 0. So that's a 0 plus 2 over e to the root 1 is e to the 1, and that's just e, plus 2 over e. And so that is our answer. We get an actual number. That means that this integral converges. And there you go. That's all you need to that's all the proof you need to establish that an integral converges, is just that it will end up equaling a number, like a real number. So we're going to go over here and do one more problem, and this problem involves a more difficult style of integration. We're not just going to be able to get away with a u substitution here. Alright, so last problem is number 28 on page 551, and we're asked to solve this integral. And so we need to ask ourselves, alright, is this an improper integral? Yes, it is. If we get 3 minus 3 here, we'll get a 0 in the denominator. So this is a discontinuous integral. So that means right away we need to write it out in proper limit talk notation. So as t approaches 3, between 2 and t, get 1 over root 3 minus x dx. Now we need to ask ourselves, okay, how can we solve this? So, well, actually, we can just get away with doing a u substitution. I just looked at this again, and yeah, we can totally do a u substitution here. So, I was going to do a fancy version of a trig substitution. That's what I have written out in my notes here. And you actually do a trig substitution where you make x equal 3 sine squared theta, and you can do a bunch of algebra and trigonometry, and it'll work out. But looks like we can actually just do a u substitution here. That was my bad. I broke my own rule of looking first to see if a u substitution works. So we make u equal 3 minus x, du will be negative dx, so we'll take care of the negative and the coefficient here. We make t approach 3 still. We'll get negative, so we put a 2 in here, that becomes a 1, and then we put the t in here, and that would be, u is going to be 3 minus t. And then this will be, or we can write it out as u to the negative 1/2 du. And so when we integrate this, we're going to get negative, and so we add a 1 here, we're going to get root u. Well, we need to bring this down, so that's going to be negative and a negative is a positive, that's half u to the 1/2. Between 1 and 3 minus t. This is the limit as t approaches 3. And so we'll get the limit as t approaches 3 of a half times root 3 minus x between t and 2. And so we plug the t in here, and then we put a 3 in for the t, and we're going to get a 0. So we get a 0 minus 1/2 times 3 minus root 3 minus 2, that's root 1. So that's minus a half. So this integral converges at negative a half, so it converges. And that is how you solve that integral. So that's it for improper integrals, and I'm pretty sure that that's it for Chapter 7 then. So thanks for watching, and stay tuned for the rest. We're plugging right on through Calc BC, and we'll be done with that pretty soon. So stay tuned.